In this video, we're looking at a Mercury light source, and the light from that passes through two slits in order to create the tightest beam possible. That beam then hits a diffraction grating, and then the wavelengths in that mixture of light are going to interfere constructively at different angles. And this constructive interference is guided by the basic equation d sine theta equals n lambda, and I'll post a link to the video where that equation was first derived. What we're looking at in part A is a particular ultraviolet emission line of mercury. That's 253.7 nanometers. I want to compute the smallest angle for which this line is going to interfere constructively, and that's labeled as theta in our diagram. So the first location of constructive interference, that corresponds to n equals 1 in our formula, and we have the wavelength. But what about d in this formula? That's the slit-to-slit spacing on the diffraction grating. What we're given in the problem is the number of lines per millimeter, and we need to turn that into the number of meters per line. So we have a little unit conversion to do. I'm going to flip this over, and I say that I have 1 millimeter, or 0.001 meters, for every 1,500 lines. When I run the numbers on this, I get 6.67 times 10 to the negative 7 meters for the line-to-line spacing on the diffraction grating. Now we're ready to solve our diffraction grating formula for the angle theta. So we divide both sides by d, that gives us n lambda over d, and then we invert the sine function to solve for theta. Again, we're plugging in n equals 1 for the first order maximum. In other words, the smallest angle where constructive interference is going to occur. We plug in lambda, that's 253.7 nanometers, that's 10 to the negative 9 meters. We plug in the slit spacing d, and when we run the numbers on this, we get 22.4 degrees. Now this wavelength is short enough where we'll actually get a second order maximum as well. If you plug in n equals 2, we find a second order maximum around 49.5 degrees. But if you plug in n equals 3, your calculator is going to throw an error for a really good reason, and this is addressed in part B of the question. So I'll say the third order maximum doesn't exist. In part B, we're asked to find the maximum detectable wavelength of light when using this diffraction grating. And the key point here is that if you're looking at larger and larger wavelengths of light and looking for their constructive interference, those are going to occur at larger and larger angles theta. So a bigger wavelength results in a first order maximum that's farther from the center line. Well, eventually you can imagine plugging in a wavelength so big that the angle for that first order maximum is 90 degrees. It can no longer be projected on the screen, and it's over. You're not going to get any constructive interference for that wavelength or any wavelength bigger than that. So we can say at lambda max, theta is equal to 90 degrees. And in fact, this will be the smallest wavelength for which a constructive interference simply can't be projected on the screen. So that angle of 90 degrees corresponds to this cut point where our wavelength has become too large for a constructive interference to be projected. Again, we're talking about the first order maximum here, since that corresponds to the smallest angle for constructive interference for that wavelength. And we find that our lambda max is simply equal to the slit spacing, which was 6.67 times 10 to the negative 7 meters. And if I convert this to nanometers, that's 667 nanometers. That's all the way at the red end of the visible spectrum. And so this diffraction grating is simply incapable of projecting a constructive interference for any wavelength that big or bigger. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.